For the next about 20 minutes, I'll talk about our inferencing framework called ATOM, and what's behind that is a collection of the kernels, which is called AITER. I think earlier today, when you hear about the keynote speech, you might realize that AMD has delivered a lot of the very good hardware. But to light up those GPUs, we actually need a very mature and sophisticated software stacks to make sure that we could leverage whatever that they offer by our hardware. So that's exactly what I'm going to present today on ATOM and AITER. Moving on to the our real challenges. Not sure if you have realized when you do actual serving, there are basically 4 different issues. The first is, say if you grab a new building block and run it, and your GPU is basically half asleep, right? So you pretty much pay the full price, but you only get a portion of your performance. And every new model that they want their careful tune code to run really fast. And there are also like too many knobs in the middle. Like when you split the model nowadays, because it's hard to fit in one GPUs, right? So how big is your batch? How much is you actually shrink your the models? What is the setting? And it's very hard for people to adjust, and a lot of the manual work has to be done on that. And thirdly, when there's like say the model that grows up and you basically outgrows one machine, and it stopped being setting and become a totally new project. And the last thing is, when there's a new model, basically you're waiting for someone to make it really fast. So addressing those 4 different challenges, we actually at AMD try to addressing them and give 4 different answers to those challenges. So for the rest, please keep those 4 challenges in mind, and that my talk will be addressing those challenges one by one. So think of this, the whole thing as basically a 4-story building. And what we actually do is I will take you, one floor at a time. On the ground floor, it's ATOM. ATOM is basically part of, that actual runs your model. The second floor on top of that is tuning. So pick up the smart way to run it. The third floor is going to multiple machines. And on the top floor is, what is the roadmap? What's next? So we can go one by one on our floor. The first floor, which is ATOM, that's the piece that does the running, right? The execution engine. And what we do is we intend to keep it really, really small. And by keeping it small and keep it open source, you take your model, whatever you like to launch it, you send it down to the fast path of our AMD hardware. So that's the design goal and design principle of ATOM. Okay, and where ATOM sits in your stack, right? I think on the top you have the tools that you're very familiar with: PyTorch, vLLM, SGLang. On the very bottom, it's our AMD GPUs. So ATOM is actually sit in the middle. That is the traffic cop for our machine. What it does is it does the scheduling and bookkeeping. And we actually intend to make it small, as I mentioned, because the world doesn't really need another very gigantic inferencing framework. We keep it as small and behind the scene. So the idea is, if you go to like a restaurant, you take the order, you talk to your Euro convenient way, and we are the one who behind the kitchen and get everything done. And that payoff is very, very sufficient, because you can see the kind of models that we basically support, from the condensed models to nowadays MoE models, from a smaller one to the bigger one. So in our blog, we actually mentioned the speed is the moat. So by keeping it small, we can, marching very, very fast. And also, as I mentioned, we do not want to reinvent the wheel. And the world has a lot of a matured inferencing engine, and using vLLM as an example. What we do is we also, tightly integrated with those popular inferencing engines so that, for you, the user experience will keep very much the same. We actually are the orchestration layer behind the scene. We, just provide the kernels and the best way to leverage the capability of our AMD GPUs. So how to do that, right? So what is the things behind the scene, which is AITER. So AITER is, basically a collection of our models, and which is also the router. You can think of that as a router for whatever the kernels that you write nowadays. I know people love Python, so they write, like, say, Trident kernels. And some people want more, manipulation, so they would like to go down a little bit to the thread level. And also, somebody might be an assembly expert, so they can write assembly kernels. So what AITER doing is we have this collection of the kernels, and we will base on the model and the situation to be able to select the most proper one of, to run our model more efficiently. With these, besides the AITER that's serving those models, we also have, additional 3 more compiler to actually be able to get more speed lever to sit on the top. The first one is, of course, quantization. For smaller numbers, actually, the less data actually are moving. With less data that are moving, that means like more speed, right? So we support very aggressive format, MXFP4, and for the weights we support A4, W4. And for those aggressive formats, we are be able to tackle like the expert-heavy models nowadays, and we even keep the running conversation in a very compact form, and we free up a serious room for our big models. For the second one is pre-computing. You don't want to just like recompute your puzzles every single time, one and one again. And what we do is we work it once, write down the steps, and then let the chips to replace them. The third part is guessing ahead, right? So we let the models sketch the next few words, right, and then check them all at once. And some of the models nowadays support speculative decoding natively, and some of them need some extra small models to run on top of it. So yeah, as an ATOM inferencing engine, we support the most popular ones right now that's on the market. So what's the bottom line after I speak so much about those design principles? What we actually delivered right here, you can see, this is the DeepSeek reasoning model performance. We basically measure up to 1.4 times of the throughput compared with our competitors. And we're basically right in the mix for other popular models. And by the way, for your information, those are the public numbers, published numbers, and the source at the end, right? So, and also, I think one more thing is, as a developer, I want to dig into the detail of it. But as a user, I'm maybe pretty lazy, right? So what I want to do is I just want to do, let's say, vLLM serve, and then the model. Does it work in that way? Just as a list of command right there. So with a few lines of a code, you just install AITER, you install the ATOM, and then you do vLLM serve. That's exactly how you run those things nowadays. Yeah. And this is the first floor, the ground floor that we talk about. And now what we do is we move on to the second floor, which is the optimization layer. So to cure basically the problem, remember I talked like too many knobs, right? So what we need to do is we need to have a very efficient optimization layer that select, say, the right kernels, and more importantly, select the right combination of that one. Pretty much, there are 2 nested loops right here. On the left, you see there's like an inner loop that works piece by piece. So basically for every single operation, every size, we hold a race between those candidates and keep the winner. On the right, there's an outer one that tunes the whole setup, right? Because optimized kernel could be a multi-dimensional search problem, and it is very hard to find individual optimals that sums up as the global optimum. So we actually, we're choosing among those settings that actually moving the needle and selected the best one. And when the model splits, right? So how big is each of the batch? What are the number formats? How is one machine over many? What are those settings? So that's what the right part is doing. So after tuning, right? So after this tuning, we need evaluation. So this is basically the three evaluation modes that how we present nowadays to validate our result. I'm not sure about you guys. For me, I think when I work at AMD, the resource, not everyone can access a whole 455, the gigantic rack that you see right there. So we always want to save some GPUs, right? So that's why we offered something that, as a quick back of the napkin estimate, there's no GPU related. And we basically, in second, we search and rule out 1,000 of the bad options. And we only evaluate those who actually need to have a real test on the real machine. And that's basically the truth. And we save it as our finalist for the best kernel. And of course, we combine the two, right? So then there's combine the two together, there's a hybrid mode that estimate a natural field that try to select the optimal result. And the next piece, right? So with all the optimization, with the individual kernel selection, the most important thing is how do I know, say, if I contributed a kernel, which is right, contributed positively. So we pretty much closed our loop with CI. Yesterday, when I was in a conversation with the community developers, a lot of the people actually talk to us and express their actually concern about the CI. So what in my mind, the CI, which is a moving kind of thing. So you have, your code that checks in, how did it affect each of the operator at the operator level, whether there's a performance degradation, whether we have like a regression kind of test, right? So those things will determine how robust your code contribution is. So for ATOM and AITER, we actually established a multiple layer of our CIs at the operator level, E2E testing, and also, as well as how this integrated into popular frameworks like vLLM and SGLang. And of course, it's not perfect nowadays. We're still developing, but the whole concept, right? So we have this thing that CI close the loop right here. Okay, so the next, I talk about a lot about the individual node. Nowadays, I think if you look at the next generation of the large language model, we're reaching to 2 to 3 parameters, 2 to 3 T parameters. The activation parameters next generation might be 150 to 250 billion, right? So those are very big models. It's very hard to be fit into one node. So that's why we need a disaggregated serving. Yeah, so I think that you are all very familiar with this concept about the PD disag, right? So basically one is reading the prompt. It's basically a math workout. And the other one is writing the answer, which is basically a memory workout. To split it up, and each side, they can grow on its own term, right? So let's let each of the chips handle the different things on what they can do the best is the current trend of the design. And to make this happen, right, what we actually need to do is make sure that our communication layer behind the scene, which is very robust, so that we can not only compute or store the data, but also we need to move the data more efficiently. So that is what we have offered here, which is called MoE, right? So MoE, it helps when when the data was splitting and just keep the KV cache in syncing. It has actually three parts. So number one is it run a big data shuffle among different experts. The second is it carried the conversational memory from like the reading machine to the writing machine. So that's how the PD Disag nowadays works. The third one is it handled the rest, the chip-to-chip communication better. I think that's one of the things when we here at AMD, we offer not only the GPU solution, but also like GPU to CPU solution. So the communication, we try our best to make sure that it's not the block for our large language model serving. Yeah. So by talking a lot about our concept design, let's look about some of the numbers here. So for, we have this expert back-to-back shuffling, and by sending out to the, between machine to machine, we're actually move the conversational memory about 10% faster than our well-known alternative. When we actually run thousands of requests hit at once, our squeeze out is about 20% more than the streaming answers back efficiently. And to basically add it up, actually I should come back to this slide. There are multiple machine setups. And so at the AMD, as I talked about it, we not only offer the GPU, but also have the CPU. So we, totally lines up a very competitive total cost against, our different competitors here. So I think we talk about the single node, the multi-node, and then the top floor, we're talking about our roadmaps, right? And of course, all the roadmaps are focused for the next generation of the chips. And as a Euro caveat, right? So these are the plans, unlike the previous, what I just talked about, are open source. It's available for you guys to try. This one is the plan, and the plan can shift. So what's coming next is basically three different layers. One is our next chips support. So for our next chip support, we support the upcoming generation of our already underway. There are basically our libraries for tuning the result, and also the new way to split the work. As disaggregation serving nowadays, like a lot of the challenger working on the expert parallelism, right? Instead of the Euro like TP, DP, this kind of thing. So we will offer, the easier to program and fine-tuning APIs and layers so that you guys can contribute a code upon. And most important thing is the flywheel, right? So when we tried it fast and provide the ecosystem so anyone can test it. So that's our commitment. As always, when I reach the end of our presentation, I like to summarize, right? So sometimes I had to go to a meeting and said, okay, what's the talking point? I think three talking points. One is, it's ready for some serious real work today. We can run the most demanding models nowadays. You guys can try, like say, DeepSeek V4, and we have the latest models like Qwen and the Kimi and those models that can be run on top of Atom. And the second is it tunes itself, right? And third, it's open source. I think I mentioned open source many times, that you can basically download. It's all on the GitHub and try it on the AMD GPUs. So that's pretty much all my presentation for today, and hopefully you guys are not sleeping. Yeah, thanks so much.